Let's look at this AP exam review, and we're focusing on the concept of limits. So let me just go through algebraic steps for evaluating limits approaching a real number. So the first thing we always do if we're trying to evaluate a limit approaching a real number, we just plug in that argument x value. If we see one side limit, we're going to ignore it for now, and we're just going to plug that in. And when we plug that value into the expression, if we're able to find a limit, that means if we're able to plug in that x value and in return we get a real number, then we have our answer. There's no need to do anything more than that. However, if we plug in into the expression and if we get a 0 over 0 in return, then that tells us that we have to continue working with the problem. A lot of times this indicates that we can further simplify the expression and then reevaluate the limit. So if we get 0 over 0, then we keep going. If the limit does not exist, then we evaluate further only if it's a one-sided limit. So if the limit does not exist, meaning that if we get a real number or non-zero over a 0, then a limit is not going to exist. However, if it ends up being a one-sided limit, then we need to provide further detail of the graph behavior. So we may have to use decimals. Okay, and if we have to use decimals, then we're going to choose between positive infinity or negative infinity, and we're going to choose a decimal that is appropriate from based off of the what's being given to us in the one-side limit, and then we plug in that appropriate decimal, and then we can therefore decide between which of the two answers, either positive or negative infinity. All right, now the steps for evaluating limits approaching infinity, what we do is we compare degrees between numerator and denominator. So if the numerator is less than the degree of the denominator, then it's always equal to 0. If the numerator and denominator have the same degree, then we simply take the ratio of the coefficients, of the leading coefficients. And if the numerator degree is greater than the denominator degree, then we know the graph is either going to positive infinity or negative infinity. And we're going to have to plug in a large representative value to help us decide which sign to choose. All right, let's look at some of these problems here. 93. Limit as x approaches -2. So the first thing we do, if we try to evaluate limit algebraically, we just plug in that target x value and see if we get a real number. So 3, -2 squared minus 2 times -2 plus 1, 17. That's a real number, so that's our answer. Limit as x approaches 5. There's no variable to plug in, so this expression will always remain 4, so that's our limit. 95. As we approach -3, we plug -3 in for x. We get -3 cubed minus 2, which is -27 minus 2, which is -29. That's a real number, so that's our answer. Okay, 96. We plug in 8 into the expression. We get 64 minus 64, which is 0. Denominator also gives 0. So 0 over 0 tells us that we have to factor and then try to reevaluate. So notice the numerator is difference of squares. We can factor that to be z minus 8 times z plus 8. The z minus 8 in the numerator is going to match the factor in the denominator, so that goes away. And then we can reevaluate the limit by plugging 8 into the remaining expression. So 8 plus 8 is 16, so that's our limit. Okay, 97. Plug 1/4 into t, and we're going to get 0 over 0. So we look to see if there's anything that we can factor and help reduce the expression. So 1 minus 16t squared can be go through difference of squares, will be 1 minus 4t times 1 plus 4t. 1 minus 4t and 4t minus 1 is essentially the same. They're just off by a factor of -1. So if I factor out a -1 from the numerator or the denominator, I can get these two factors to match. So if I pull out a -1, then the remaining expression will be -4t plus 1, which is the same thing as this expression here. So then when we cancel out, don't forget there's a -1 remaining in the numerator. We reevaluate, plug 1/4 in for t. 4 plus 1/4 is 1. 1 plus 1 is 2, so negative 1/2 is our limit. All right, 98, we're going to evaluate the limit here, or evaluate the limit. So plug negative 2 in, we're going to get 0 over 0, so we're going to factor numerator and denominator. So we see factors of x plus 2 show up repeated between numerator and denominator. We can cancel those out, and then we can reevaluate the limit. Plug negative 2 in for x. Negative 2 plus 3 is 1. Negative 2 minus 2 is negative 4, so negative 1/4. Okay. 100. Limit as x approaches 0. Plug in 0 into the expression. We're going to get root 2 minus root 2, which is 0 over 0. So this is a problem. We should be able to recognize this as a conjugate problem. So multiply numerator and denominator by the conjugate of the numerator. So the conjugate of the numerator is going to be root 2 plus x plus root 2. So the only sign we change is the sign between the two expressions. This sign inside the first radical does not change. That stays as root 2 plus x. All right, so then we distribute and expand. So root 2 plus x times root 2 plus x will just be 2 plus x. The middle and outer terms will cancel out. And the last terms, negative root 2 times negative root 2 is negative 2. The 2 and negative 2 cancel out. The x and x will also reduce. We're left with 1 over root 2 plus x plus root 2. And then we can replace the x. Now we can reevaluate. Plug 0 in for x. Root 2 plus root 2 will be 2 root 2. So 1 over 2 root 2 is our limit. Uh, 112, we have piecewise function. Two branches. One branch of the graph is going to be to the right of 1, and then the other branch is going to be to the left of 1, and they may or may not connect at x equals 1. So let's look at part A. As we approach 1 from the right side of 1, so we're looking at the one side limit, and from here we have to decide which of these piecewises will be appropriate to match the condition in the piecewise. So to match the condition, we're approaching 1 from the right side of 1, so that will be a better fit for the first piecewise. So we're going to evaluate the limit as x approaches 1 from the right side of 4x minus 2. Remember, if we see one side limit and we're trying to evaluate the limit algebraically, we just plug in that x value and see what we get. So plug 1 in for x. 1 times 4 is 4. 4 minus 2 is 2. So 2 is a real number. That's our limit. 112. Plug 1. First off, we have to decide which piecewise function to choose. We're going to approach 1 from the left side of 1. So from the left side of 1, it'll be with the second piecewise. So limit as x approaches 1 from the left side of 1 for 2 minus 4x will be negative 2. Plug 1 in for the x, negative 2. So from the right side of 1, the limit, the graph is approaching the y value of 2. From the left side of 1, the graph is approaching y value of negative 2. So that's why part C, when we're trying to evaluate the limit as x approaches 1, is undefined or does not exist. Because in order for a limit to exist, the graph has to approach the same y value from either side of that target x value. So from the left side of 1, the graph is approaching negative 2. From the right side of 1, the graph is approaching positive 2. So there's a disconnect. This is going to be a non-removable discontinuity. So limit does not exist. Part D, we're simply just looking for the ordered pair. So f of 1, so where is 1 defined? 1 is defined based off of the condition, and restriction based will be for the second piecewise. So if we plug 1 in for x, 2 minus 4 will be negative 2. So that's our ordered pair, or y value. Okay, so we have one more piecewise function here, a of x. So split between three expressions here. So 3 minus 6x. This is the branch to the right of 1. We have an ordered pair y value right at 1. We also have another branch that exists to the left of 1. So again, one thing that we have to decide when we work through this problem is the graph going to be connected through 1, since there's a left branch, there's an ordered pair of 1, and there's a right branch, ordered pair, and a left branch. Okay, so if we're approaching 1 from the right side of 1, we look at our restrictions to see which one is appropriate. From the right side of 1 will be for the first piecewise, so we're going to plug 1 into the first expression. So the first thing we do is we ignore the the one-side limit, just plug in the x value. So 3 minus 6 is negative 3. As we approach 1 from the left side of 1, based off of our restriction, it will be matching with the third piecewise function. So limit as x approaches 1 from the left side of 1 for x squared, plug 1 in for x, 1 squared is 1. As we approach 1 from both sides, we see that the graph is not going to be the same y value. From the right side of 1, the y value is negative 3. From the left side of 1 is positive 1. One thing that we don't care about is we don't care about what's happening right at 1. This is not going to be relevant in determining what the limit is. So we only care about the left branch and the right branch, and we see that as they approach 1, they're not going to connect to the same y value, so therefore the limit does not exist. All right, we're looking again for the order pair. What is the order pair at 1? Well, 1 is defined for the second piecewise, so plug 1 into the expression. There's no x to plug in, so the second piecewise is always going to be just that order pair at negative 1. So a of 1 is negative 1.